Okay, welcome back to the video lecture series again on basically how to compute statistics. What we will be doing in this video is the one-group t-test, but we have to talk a little bit more about samples and populations in order to do this. Because, as in previous videos, we indicated that the other videos we were dealing with a special population. What I mean by that is we had measured all of the observations possible in an environment. We were only dealing with that environment. We were not extending to other possible environments. This is going to be another case like that where we can assume a population basically based on probability, so we don't have to make all the observations because probability tells us what those observations will be. So we will be able to assume some population parameters. I'm going to bring up an entire story problem here. What I'm going to do is just kind of generally tell you what's going on. I encourage you to read through it. This is loosely based on some actual research that's out there, but what is the situation? Well, the question is that there are species of birds, in this case scrub jays, that actually collect some food and then they go and hide the food. They've got different foods that they can eat. In this case, we're dealing with mealworms and we're dealing with nuts. The problem with mealworms is that they decay rapidly, naturally, and as they decay, they go bad and they get, quite frankly, nasty. Whereas the nuts are going to last a lot longer, but the trick here is that the birds really prefer the mealworms to the nuts. So, as they are hiding food, we want to really understand two questions with the scrub jays. The first question is, do they remember where they hid things, where they hid food, and what they hid in the locations where they hid it? The other thing is, do they have an understanding of time and decay? So, if we think about this, if you gave them, again, don't worry about the true experimental design here, we're gonna make a lot of assumptions. But if you gave them an equal amount of nuts and mealworms and a location, an area spread about that they could hide this in, so here's the conceptual idea of what's going on. You give them the food, their natural instinct is to go bury all that food. So I've given them the same amount of nuts as I've given them in terms of worms. They go and bury all of these worms and nuts. If they understand time, then we're going to end up breaking this into two experiments, although later we'll see that it's actually better if we do it in one. But for now, we're just learning statistics, so we'll break it into two. So, if they remember where they buried things, then let's start with the first experiment where we just make them wait for 4 hours. If they remembered where they buried things, and they do prefer the mealworms, then what's going to happen is what we would expect them to do is actually go and selectively dig up more of the mealworms than the nuts. That's our experimental hypothesis. But remember, in statistics, we often want to talk about in terms of null hypothesis. So what does this mean? If they don't remember where they buried things, what would happen? Because that's what's really driving the question here. If they don't remember and we just let them loose and they're digging things up randomly and they buried things randomly, then 50% of what they dig up we would expect to be mealworms and 50% we would expect to be nuts. So that's how we get the population parameter based on probability. 50% is probability tells us if the hypothesis doesn't fit and doesn't work, then things should be happening randomly by chance, and in this case, random chance dictates 50%. So we can use at least one population parameter in our statistics, and that's what we're going to do. But imagine if we did that 4-hour study, we delayed them 4 hours, and they just dug up mealworms. Does that necessarily prove that they know that the mealworms decay? Not really. All this really tells us is that they are digging up the food that they perform more. It doesn't tell us that they know that they decay and that later they should dig up just the nuts. So that's why we would have to do experiment 2, which means that in this case, the other group, we would actually make them wait for 124 hours before we allowed them to dig up food. Again, if they know nothing and it's pure random chance, we would still expect them to dig up 50-50. When they dug up the nasty mealworm, they would discard it and not eat it, but still in terms of actually digging it up, we would expect it to be 50-50. that would give us more evidence in favor of our hypothesis. So this is kind of what we're going to be working with and developing our statistics and our experiments on. So before we move on to the next slide, what I would like you to do is basically pause the video at this point, try to create your null and experimental hypotheses for both the 4-hour experiment and the 124-hour experiment. Okay, if you've paused and you've come back, I will actually provide you with those. Basically, experiment 1, we are again going to be looking at a sample, so we will have X bar, and we are going to be comparing it to a population mean. So again, a population mean is always indicated by mu. And if we write that in English, then basically we are saying the percentage of worms, we're just arbitrarily picking worms in this case, dug up by the birds will be equal to 50%. Our experimental hypothesis will be the percentage of worms, the X bar for that sample, will not equal 50%. Experiment 2 is basically going to be the same thing, but the outcomes would be expected to be different. So again, the number of worms or the percentage of worms dug up will be equal 50%, whereas for the experimental situation, the number of worms dug up will not equal 50%. So let's just now start with and work with our data for experiment 1. I have 12 different birds as indicated by B1, B2, B3. What am I saying there? That's not a variable really. It's just shorthand for bird 1, bird 2, bird 3, etc. So bird 1, the percentage of worms that bird dug up was 73%. Bird 2, they dug up 82% of what they dug up was worms. That's what we're looking at with this data set. Later, we will come back to experiment 2 and you'll have a chance to try to work out this data set on your own. So as we move forward, we are going to be doing what we did before. If you learned and understood how to do a one-group z-test, a one-group t-test is virtually identical. We are just in some parts of the formula dealing with population and in other parts dealing a bit more with samples. So what does this mean? With a z-test for a group, we knew the population mu, the average for the population. We also knew the standard deviation for a population. In this case, the only population parameter that we actually know is mu. That's that 50% probability. There's no way that we can determine what the standard deviation, the expected deviation from that 50% would be, but we can estimate that with my sample. So we're going to use the sample to estimate the population parameter. Anytime we have an estimate, our confidence decreases, but if that's all we have, then we just have to move forward with a slightly decreased confidence, and we're going to find that we will compensate for that a little bit later down the road. So let's look at the formula that we've dealt with before. If you remember this, we had the z-test for a group, we had x bar minus mu, we had the standard error for that denominator. To get to the standard error, we had to go through the standard deviation, which we already knew in this case, and we calculated that formula. But as we move forward and we look at the one-group t-test, the formula is identical, but instead of the population standard error, we're going to have the sample standard error. We're just going to estimate based on our sample, but to get to the standard error for the sample, we have to, just as before, go through the standard deviation, but in this case, we're going to use the standard deviation for the sample that I just showed you. So as always, as before, build your toolbox and fill it in. We have added something new. In this case, it's the degrees of freedom. I will explain what that is in a moment, but in this case, it's going to be little n. So if you remember correctly, little n is the number of observations for the sample. Remember, the formula for calculating an average, as we did before, is just sigma x divided by the number of values. In this case, we're dealing with a sample, not a population, so that's going to be little n. So you just do what we've done before. This is very easy. We just add the values to get sigma x. We count the number of values to get little n. I encourage you to pause the video, take a moment to calculate that, see if you get the same value. As we do that, we're going to then put it into our toolbox, and I'm going to give you the value very soon in the next slide, because remember, the first step is always deconstruct your formulas. I need X bar in the toolbox, but when I look at the X bar formula, I'm going to be dealing with sigma X and sigma N, so I put those into my toolbox. So I need to do the same thing with the standard error. I'm going to deconstruct the standard error. What do I mean by that? To get standard error, I need standard deviation divided by the square root of n. Do I already have standard deviation? That has not been provided for me, so I need to deconstruct standard deviation. So as I move forward, I know that I'm going to need to calculate the standard deviation. To get to the standard deviation, I need sum of squares, and I, of course, need little n. As before, as I told you, mu is going to be 50%. I have not provided the formula for sum of squares because we've covered that before. If you're looking at this manual on your computer, just go ahead and click this link. It will take you back to it if you need the review. So again, the sample standard deviation is going to be computed as we have before, and this will serve as an estimate for the population standard deviation. We have to learn something new first, though. What is degrees of freedom? Why have I added that to the computation? Well, there are a number of ways of looking at the issue of degrees of freedom, but a simple one kind of goes like this. Populations are theoretically infinite, and consequently, the mu average is never truly calculated. If I have an infinite number of values, I can never plug the last value into the formula. So because it's never actually calculated and it's got an infinite number of values, mu could always be something different. As I run across more values, that could change slightly the overall computation of mu. However, once you use a sample to estimate the population parameter, then mu becomes known. Remember, if it's an infinitely large, mu could always change slightly as I add numbers. But as soon as I say that mu is such and such, because I'm estimating it with my sample, mu becomes a known quantity. Once mu is known, then we're going to find that at least one other number becomes locked in, or it loses its freedom to vary. So let me try to describe this. Imagine I use this sample to estimate some population parameter, in this case mu. So I calculate my sample mean, and if that is going to be my estimate for mu, mu is now locked in at 41.38. But remember, this is my sample. That sample could have been any group of numbers. It could have been this group of numbers. But if I've already said that x bar equals 41.38, then these numbers can be anything that they want. They can be anything, but if x bar is 41.38, then I already know that sigma x needs to be 538. Looks like I've got a small error on this slide. That should read 538 instead of 53. So if I've already estimated and locked in 538 and 41.38, even though these 11 numbers can be anything that they want, that last number can't be. In order to come up with sigma of 538, that value in this instance must be 22. If I picked another group of numbers, then they could be anything that they want but that last one. The last one would have to be whatever is required to get to 538 and consequently a mean of 41.38. So this is what we mean by if you estimate a population parameter using a sample, you have locked in that population value. It becomes a known quantity. Once it becomes known, all the numbers can be whatever they want to be except one. One of them loses its ability to vary and becomes whatever is dictated by the rest of the numbers and that value that you've estimated. So in this case, we're using a sample to estimate one population parameter. What do I mean? Mu, we had decided, was 50% based on probability. But we did not know what the population standard deviation was, so we said we're going to estimate that with our sample standard deviation. Once we estimate it, we've locked in that value, so we lose a degree of freedom. So our degrees of freedom for a t-test is the number of observations minus 1 degree of freedom. If we estimate, as we will later on in the video series, a couple of population parameters with 2 samples, then we will end up losing 2 degrees of freedom, because for each of those estimates, one number gets locked in. I hope that helps you understand it. Some individuals find it a very easy concept to grasp, others not so much, but it's pretty straightforward as long as you remember for anything that you estimate, for any population parameter that you estimate using a sample, you're going to lose at least 1 degree of freedom. So we go back to our statistic again. I've got my t formula, x bar minus mu divided by the sample standard error. I deconstruct my sample standard error into standard deviation, sample standard deviation divided by the number of observations for that sample. And then I can further deconstruct that into standard deviation, which is the sum of squares divided by n minus 1. And of course, I need to compute my sum of squares. So in order to do this, I've provided you a template to help try to remind you how to calculate that sum of squares. And as we move forward, we will take those values and use those to fill in our toolbox. Once you've filled in all of the blanks in your toolbox, you should be able to calculate your final t value. I've already filled in here on the actual numerator because we calculate that mean for that sample to be 85. Remember I told you before mu is going to be 50, but ultimately I'm asking you what are the values to go in the rest of these blanks. We now have to, with a t statistic, we have to report it with the associated degrees of freedom. So in this instance, you'll see t, open parentheses 11, because we have 12 observations minus 1 degree of freedom. So t for degrees of freedom 11 equals some number. So I'm going to try to get out of the way here. I encourage you to pause the video, actually take a moment to try to calculate all these through. When you come back, I will show you all those answers. Now that you're back, these are the answers that you should have calculated. Once you calculate t of 11 equals 11.71, you now have to ask yourself the question, do I reject that null hypothesis or do I fail to reject? Just as before, I'm going to have a distribution with the fail to reject region and the reject region. However, this is no longer the z distribution. With the z distribution, because it's based on infinity, it is locked, it is set, it is not going to change. But the t distribution is an estimate of that infinitely large standard unit normal distribution. So we have to go to what's known as the t chart, the t crit values to look this up. When you are looking at this, I want you to notice that I've got the degrees of freedom listed over here. Ultimately, we are going to be dealing with 11, but right now, what I want you to notice is at the very bottom, I've got infinitely large. Then as we look at here, as we go across this way, I am looking at the alpha level for a two-tailed test. We've been using alpha of 0.05, so if I look at alpha of 0.05, follow that all the way down to an infinitely large sample, note that my critical value is 1.96. So a z distribution is an infinitely large sample. That's what a population is. But we aren't dealing with infinity. We'll never get down there. So what we're going to be dealing is with a sample size of some value. So as we get smaller than infinity, you'll notice that my values start to get a little bit larger. What that means is if we started with 1.96 for my critical value, if that value gets larger, it's going to push that number line out farther, which means that it's a bit harder to get to the reject region. Why are we doing that? As I move from an infinitely large sample to a sample of 100 or 50, my confidence obviously decreases. As my confidence decreases, then what happens is that changes the shape of the distribution and the criterion for significant gets harder to achieve. I want to make sure when I'm less confident that I've reached a higher threshold of significance. So in this case, once we look at our actual degrees of freedom of 11 with an alpha of 0.05, that's going to give us our critical value that you see here of, because it's two-tailed, plus and minus 2.201. So now we've got our critical region set at plus and minus 2.201. Our actual t-observed value with degrees of freedom of 11 was 11.71. That puts us solidly in the reject the null hypothesis region. So this means that it provides evidence supporting our initial hypothesis that the birds in fact do remember what they buried and where they buried it. But this experiment with just 4 hours does not necessarily indicate that they know about time and that food will spoil. That's why we need to do the other experiment with the other group of birds where they actually have to wait 124 hours. These birds dug up more worms because we know they like worms, so they remembered where they buried it and they dug up their preferred food. Only if they know that the worms spoil will nuts then become the preferred food. So experiment 2, nuts will be the preferred food, and we would actually expect them to dig up fewer worms, and if that is the case, we should find a significant value down here, significantly less than 50%, instead of significantly more than 50%. So this leads us to experiment 2. We've created the hypotheses earlier. This is the data for that second group of birds. We've deconstructed the formulas just as before. We've built the toolbox. You're going to need that critical value based on the degrees of freedom. So you'll need to calculate your t observed. You'll need to decide whether to accept or reject the null hypothesis. And then you will need to interpret what those results that you found mean. So again, I encourage you to pause the video, start from absolute scratch on this one, and see if you are able to compute this through without looking at previous examples, but just looking at the formulas and reading what the formulas are asking you to do. If you've paused the videos and computed on your own, these are the values that you should have come up with. What I discourage you from doing is bringing up the values and calculating while the values are on board, because what that basically causes individuals to do is work both forward and backwards. If they're working forwards and it doesn't look like it's coming out where it should come out, then you're not basically making sure that you're following the instructions. You're getting a hint ahead of time. You want to work it all the way through, then find out if it came out right or wrong. If it didn't, then you can go back and find out exactly what went wrong and where and why, and then make a mental note to yourself to not make that mistake again. So again, this statistic looks identical to the z-test, but now instead of dealing with a population and the population notations for the standard deviation, computations are identical with the exception of you are using n-1 for degrees of freedom with that sample. You're doing the same thing, you're just using different notations because you're now dealing with a sample and you lose the 1 degree of freedom, but again, the computations are identical. So as long as you've learned and got it locked into your head early on, I encourage you to practice a lot. If you learn the first steps, these later steps are going to be absolutely easy as we move forward. Again, thank you for watching the video series, and I hope that this is helping you.